Okay, you guys, here we are, Wednesday. I've put some new readings up, 7.3 and 7.4, and Friday we're going to move into classes for the first time, structures and classes. And I'll probably put an assignment up on Friday, but it's not quite ready yet. Today I'd like to spend some time talking about homework 5, just finishing off, I guess, everything that you could possibly want to know. And then Madeline will do her thing, and then if there's time at the end, I will move into the chapter 10 stuff on structures and classes. Any questions before I get going? So let's pull up the homework 5 that's due Friday and talk about some of the details of this assignment. So remember, you kind of have to meet all of the conditions that I've spelled out. So make sure that you read each one of these very carefully and try to implement as many of these things as you can into your homework. And then don't forget about the above and beyond. Above and beyond can be a modification to the cellular automata rule. It could be, perhaps, I don't know. I'm trying to think of, you could try different boundary conditions. For example, instead of using these periodic boundary conditions, which I'll talk about today, you could do some other thing at the end that's perhaps not periodic. But whatever you do, make sure that you tell me in a comment at the top of the main program. All right, let's talk about the pieces of this program. As I mentioned, I gave you the main program, and that's the program that's what I would expect to see in your main program. Your main program is going to declare an 8 integer array, and you're going to pass that array into the getRule function. Does anybody know what a prototype looks like for passing an array into getRule? So that's the first thing I want to talk about. So this is in section 7.2, I believe. We have getRule, which is a void function. And the prototype for that guy might look something like this: int, just like that. Int with empty square brackets following it would be a suitable prototype, or declaration. That's the other word that we use. So let me put here declaration. I use those words interchangeably. The book tends to like the word declaration. This is a signal. So remember how the declaration works. You put it at the top of the program before main, and as the compiler is going through, it says, "Oh, here's a function, getRule, and its argument should be an integer array." But notice there's no dummy variable. You don't need a dummy variable name. You don't need to name the array at this point. So the signal to the compiler that you're supposed to get an array in that slot is the presence of those empty square brackets. Oh, come on. The details of passing a two-dimensional array or higher dimensional arrays I'll leave to you to read in the book. We're not going to do that probably at all in this class, but it's certainly possible. This is how you do a one-dimensional array. Down below, so here's main. Down below you would have your definition. And there you actually have to name a dummy variable for get rule. And I would just use the same name, R. And then inside here are the steps for defining get rule. What does get rule have to do? Go ahead, Dylan.
So it has to, sorry, you have to that C and peak function, right?
Yes, yeah.
Because
we're offering a default value, yeah. So
basically, it prompts the, so first it shows up as a user function. It prompts the user to be like, input a number and then provides them the default.
So we're going to get a rule number and we're going to provide a default.
Yeah.
Oops, provide. Bless you. And you guys know how to do that now because you had to do that in the bisection method problem, right? You had to offer a default tolerance, and if the user just hit enter, then that's the tolerance that you would use. But if the user typed some other value in there, then you would read that value and you would overwrite the default. Remember, the default here is rule 110. Jason.
So you actually put that inside of the function definition as opposed to above?
Yep. Okay, so we get the rule number and we've got all these conditions offering defaults. We want it to stay between 0 and 255, yada, yada, yada. Then what?
Well, then, so is that include like the while loop that'll probably be in there, right?
Yeah, there's probably going to be a while loop to keep asking the user for a value until it falls between 0 and 255. Yeah, that's all kind of in there. But that's all stuff you've done before. So let's say now we are at the point in the program where we have the rule.
Oh. And the second function is generate CA, right?
Mm-hmm.
So in that case, wouldn't this function use that rule to, or is generate CA going to make it and output it, like the automata? Okay.
Look at the argument. We haven't really used the argument to this function yet, have we?
Oh,
so what's the role? What's the other big job, Sarah?
You have to like define the rule matrix.
Yeah, I have to set up the rule matrix. So the other thing is to fill the rule matrix, or the rule array. What does it mean to fill the rule array? So I'm going to sort of bust out of this function here and just look at R0, R1, R2, up to R what? 7. This is an 8-integer array, index 0 to index 7. What does it mean to fill the rule array? How am I going to fill it? What am I supposed to do? Danielle.
Turning the rule number into binary.
Yep. So here we put the binary digits of the rule number. So in R0 is the least significant binary digit, and in R7 is the most significant. Right? And I gave you an algorithm a couple times ago on how to do that, right? You take the remainder after division by 2, and then that's the least significant digit. Then you divide by 2, and that gets you the next one, and the next one, and the next one. How many times do you do that? 8 times. Yes, Danielle.
So, you know how when we were doing it before and it kind of did it backwards,
Mhm.
so when we printed it, we just printed it backwards?
Yep.
We don't have to flip it, right? Isn't it not really matter?
It doesn't really matter. So now all that really matters is that in your head you know that the least significant is R0 and the most significant is R7. And I'll talk a little bit about where that comes into play in a minute. All right, so the binary digits of the rule number are now in the array. Does this function have to do anything else? No, it doesn't. Now, a little bit of a side note here. Remember we talked about pass by reference, pass by value? And if you pass an argument to a function by value, then the function can do all kinds of things to that argument, but when you get back out to the calling program, none of those changes are going to be preserved, because the function's working on a copy of the argument, not the actual argument. Arrays aren't like that. You always pass in the original array. So, all of these changes that we make, perhaps at this step, these changes are preserved. When we return to the main program. So let's go back and look at what the main program is supposed to be. So I declare R8 at the top of main. Then I pass R into getRule. What happens inside getRule? We just discussed that. One of the things that happens inside getRule is all of the entries in the rule array R get set to 0s or 1s, depending. Now I come back out of getRule, and I go to generate CA. What is in this R now? The bits of the rule number, right? The binary representation of the rule number. So when I call generate CA, I now have the rule array at my disposal, and it's been properly filled with the binary digits of the rule number. Yeah? Okay. So let's talk about generate CA. We talked a little bit about this last time, but I want to finish it off. The declaration of generate CA is going to be really similar to the declaration of getRule. Right? It's a void function. Its name is generate CA, and it takes one integer array. So there's not much there, not much new there. Down at the bottom, we talked last time about what should happen in generate CA. It's a big while loop, and the while loop runs indefinitely. And the first thing that happens is we print some row array. The next thing that happens is we compute B, which is essentially the next generation. Three, we are going to copy B to A. In other words, we're going to overwrite the array A, and then we're done. We do this over and over and over again.
So like the for loop for that would just be t greater than 0?
For in here, maybe? In here? Here?
For the printing.
For the printing. So if you'll remember, and let me show you a little bit more detail about what my main looks like. Look at the top here. I've got these various defines. The first one is the cellular automata size, and I have it set to 80. What does that represent? What do you think that means? Well, there's a comment there. Okay. So this tells me that there are going to be 80 cells in a particular row that are either alive or dead. So to print out A is going to be a for loop, and it's going to start at 0, and it's going to go up to CA size -1, right? Yeah, 79. So from 0 to 79. Okay. And similarly, down here for copy, how are you going to do the copying? Sarah? So have a for loop BI equals AI. Sorry, AI equals BI. AI equals BI, and then go from I equals 0 to 79. That'll capture every cell. Now, am I going to use 79 in my program? I'm going to use CA size. So that if at some point later I'd like to have a wider screen, I can just go up here, change it to 120, recompile, and I've written everything below in terms of this one constant CA size, and I don't have to go searching through the whole program for an 80 or for 79 or what have you. So we have these 3 steps. I feel confident that everybody in here can do 1 and 3. I want to expand a little bit on 2. Oh, and this while loop. There's one other thing that I have to do in this while loop. Talked about it several times ago now, so it might not be fresh in your memory. Yes. This is going to delay the animation. Otherwise, it'll run too fast and you won't really get the right effect. And you can go back a couple of times, look at your notes about how to do that. But you put usleep in there, which is really mu sleep. It sleeps for a certain number of microseconds. 1 million microseconds being 1 second. And this will cause the loop to pause long enough for your eyes to actually see the most recent generation. What happens in step 2? All right. I want to go back now to the description of these one-dimensional cellular automatas. And I want you to think about this guy is the rule array. This is the rule array for rule 30. Which of these is the least significant? Which of these is the most significant bit? Least significant is first, and then we have increasing significance out to this guy. Which one of those is R0? The farthest right one is R0, and then this is R1, R2, R3, R4, R5, etc. This is by design. It's not an accident that we set it up this way, because let's go back here and look at what I'll call the stencil. So consider the stencil for BI. So here you have not all of A, but perhaps a segment of A. And here we have B. And right here is sort of our generic BI. And correspondingly is our generic AI up here. The stencil for BI is the set of cells that are interacting. It's those three cells above that feed in and determine what this cell below is. Does that make sense to everybody? That's the stencil. This is by no means the only way to do one-dimensional cellular automata. You could have a stencil that's 5 wide, or a stencil that's 2 wide, or 1 wide. It'd be pretty boring, but you could do that. So this is the stencil that we happen to be dealing with in this class, in this assignment, but other stencils are possible. This is a I minus 1. This is a I plus 1. Now, what do we know about these three guys? We know that they are either 0 or 1. So together, AI minus 1, AI, and AI plus 1 form a 3-bit binary number. And we are going to say that AI minus 1, and this is not really important, but we're going to say that AI minus 1 is the most significant. Down to AI plus 1, least significant. Again, I can't emphasize enough, we don't know what value these guys have. We know that it's one of either 0 or 1, but we don't know while we're running this program what those values happen to be. If this is a 3-bit binary number and it goes from most significant to least significant, left to right, what's the place value for this guy, AI minus 1? What slot does it represent? Yeah, so that's 2 to the what?
In this case?
In this case.
3.
Close. This is 2 to the 0.
All right.
So, can you give me a formula that will convert the 3-bit binary number to an actual number, an actual integer? A formula in terms of the AI minus 1, AI, and AI plus 1. Yeah. I just multiply AI minus 1 by 2 squared plus AI times 2 to the first plus AI plus 1 times 2 to the 0, which we happen to know are 4, 2, and 1. So we can convert this it to an integer value, which I'll call, let's just call it j. J is 4 times AI minus 1 plus 2 times AI plus 1 times AI plus 1. What's the biggest that a 3-bit binary number can be? 7, right? 1, 1, 1. 2 squared plus 2 to the first plus 2 to the 0 is 7. 1, 1, 1. What's the smallest it can be? 0. This is not. It's not an accident that we're working with R8. What's the range of indices for R8? R has indices from 0 to 7. 3-bit numbers range from 0 to 7. We'll use J as an index. in R to set whether BI lives or dies. So let's go back up here to the stencil. In the stencil, I know these three values. I know the top three values. I don't know them in terms of the algorithm, but at this point in the program, they're set. What am I trying to figure out? I'm trying to figure out this bottom value. What's the process for figuring out the bottom value? So, sorry?
Does that depend on the rule?
Sure does.
Yeah. So what rule are we using here?
The one, whatever's in R.
Okay.
So what's to compute BI, what do? I convert AI minus 1, AI plus 1 to an integer. And we know that that's going to be something between 0, 1, up to 7. And then we let BI, let's call it an integer j. And then I'm going to let BI equal RJ. Two-step process. It doesn't have to be 2 steps. You can actually merge it into one in your code. I want to do this for every BI, so what do I have to do? I have to do a loop. And there's a slight problem with this. So I have to do this for every I between 0 and CA size minus 1. For example, if I is equal to 2, then the stencil looks like this, B2, and then above we have A2, A3, and A1, right? And if it's B3, so these guys are grouped together here for this. And if it's B3, which is sort of below A3, then I have a slightly different set of guys that are interacting, like that. And this just slides down with the for loop. Okay, so the for loop does the one stencil, then slides it over one, and does the next stencil, slides it over one, does the next stencil. And for each stencil, you're taking the top 3 values, converting them to an integer, taking that integer as an index in R to determine whether B should live or die. And how does this depend on the rule, Dylan? Or on the number?
Yeah.
Do you see how now? Ish?
I get that. So now every time you're changing, whenever you change the number, yeah, I mean, that'll change, right?
Yeah.
But so every time you change the number at the top, that will pop back in the, okay.
So I have to, if I want to change the rule number, I've got to start the program all over again.
Yeah.
Get a rule number, fill the array R.
Based on that rule.
Based on that rule number, and then go in here and do this. So that's how the cellular automata depends on that rule number that you punch in. It's actually fair number of steps between that rule number and this live or die step. Everybody with me? All right, the last thing we want to deal with is the so-called periodic boundary conditions. This is all well and good. These stencils are lovely for B's between what and what? Between 1 and 78, or 1 and CA size minus 2, right? But at 0 and at CA size minus 1, the stencil pokes off the end of the A array. Does everybody see that? I'll draw you a picture. So let's say we're down at the end. So we have, or it's easier to do it at the beginning, I suppose. So we've got A0, A1, A2, etc. And now we're interested in filling B0. What's the stencil for B0? Well, it looks like this. And there's a question mark here. What do we put there? Because there's no part of the A array that we can fill in there. For periodic boundary conditions, what you do is you go way out here to A, CA, size minus 1. And you take that guy and you put it in here. Have you ever played like old arcade games? Pac-Man, Asteroids, anybody seen that kind of stuff? When the ship goes off the left side, where does it come? It reappears on the right side. So what you have there in the game of Asteroids, or when the Pac-Man guy goes off the left-hand side and comes back in on the right-hand side, what you have is somewhere inside the code that runs that game is something very much like this. Sebastian?
Doesn't that mean that in your cellular automata that the B0 cell is going to be determined by something that's not actually its neighbor?
Yes. And so the way you can think of this is, let's pretend the top edge of this is a cellular automata, is the first row. I can think of it as a cellular automata on a cylinder, where they're flowing down the sides of the cylinders. There are other boundary conditions that you can put on this thing. For example, a really simple boundary condition, what we call homogeneous boundary conditions. Anybody care to guess? In linear algebra, homogeneous evokes what? Come on, linear people. It evokes zeros. Yes. Homogeneous boundary conditions, you'll just put a 0 here. And just say that part of the stencil at the edge here is always 0. And then at the other end, when it sticks off the other end, that's also 0. Homogeneous boundary conditions. I like the cylindrical or periodic boundary conditions because then you still have a way of kind of making sense of what's happening. So my suggestion when you're generating when you're generating B, is to deal with 3 cases. Do the B0 case, where you just kind of manually figure it out here. B0 is going to be 4 times A CA size minus 1 plus 2 times A0 plus A1. Notice I'm merging the 2 steps. I'm turning the 3 bits into a number and just shoving them directly in as an index for R, all in one step. And then whatever R is for that index, if it's alive, then that'll be a 1, and if it's dead, it'll be a 0. 3 cases. Then the middle case, the most generic one, you do this for I equals 1 up to CA size what? Minus 2. And then the last case, CA size minus 1. And I'll let you figure that out also, but it's similar. Questions?
Yeah. So does this count as an above and beyond?
Maybe. What?
I just, instead of like putting zeros in there, you have to use zero, but it just counts as above and beyond.
No, I want periodic.
Oh, you want that?
Yes.
Okay, sorry.
You could think of other boundary conditions. But yes, I'm asking for periodic.
Okay.
Testing. How do you know that you're getting the right thing? Let's talk a little bit about debugging and testing. There are two functions in main here. That suggests if you're building this thing, where is it? There we go. I should write these two functions separately. I should write getRule and focus on it and make sure it's doing all the right stuff, offering default values, restricting the range to 0 to 255, and setting the rule array. So without thinking about generate CA, you've compartmentalized just getRule. GetRule, make sure that it's doing all those things, and then a good thing to do would be to run getRule, punch in a rule number, and then print out the contents of R in main and see that they're set correctly. And if you do all of that, you're ready to do generate CA. In generate CA, build the while loop. Try to get it printing out the rows of A, perhaps. So it's just really boring, same row after row after row. Then introduce the second array and maybe do the copying. So build this whole thing up in baby steps is what I'm saying. I'm encouraging you to do. Madeline, are you ready? Okay. I'm going to break there, let Madeline do her thing, and if I have any time left, I will finish up with a bit of a demo of my program. Do you need my computer, Madeline, or do you need any computer?
Yeah.
Okay. All right.
Okay.
What's your question?
What is HTTPS?
Oh, yeah. It's why Facebook is slow.
Okay.
Let me know when you're ready.
Yeah. Okay. So this is kind of what I'll be explaining, but HTTPS is the secure form of HTTP, which is what we use to kind of write everything on the internet. And basically what it does is prevent and protect against sort of like people from being able to intercept any information that you put into that you're sending to something else, so like a web server. And so what happens is, so this example is kind of like over here you have something that you might be typing in like a password, and it's encrypted into some string that someone who's in the middle that might be trying to get to won't be able to understand. And then to get to the server that you're trying to get it to, it goes through another decryption. And so these can be like different encryption and decryption processes, so it doesn't necessarily follow like the same protocol each time. And so it basically just adds security to any information that you're putting into a web page. And it was originally used for like payments online and stuff like that. And so the biggest, okay, so this one doesn't have it, but I guess, okay, and even for emails too. So as you can see, like here, it says HTTPS, which means you're on a secure web page. And basically, that just means that, so in order to, like, I guess, basically, so it's, HTTPS is like two separate protocols that are overlaid on each other. You have your regular HTTP protocol, and then when that's like SSL, TLS, I forget what it stands for. It's like transfer layer security or something like that. And so that's basically the encryption protocol, which is responsible for getting all this encryption done. And so I guess for websites that use HTTPS, they can't. So like you have to have the entire website be under HTTPS control. You can't just have like some parts of it because that will leave any information that you put in vulnerable to like interception. And one kind of interesting thing that's somewhat related is that recently there's been this problem with like Chinese hacking and being able to like cyber hack into I guess this article talks about U.S. media, but I guess it's been kind of a more recent issue that Chinese hackers are able to kind of get information that isn't necessarily secure over the internet, and so using HTTPS instead of HTTP is important for our security, I guess, online.
Questions?
So why is it important to have it for the whole website, not just the login page? Isn't that the sensitive information?
Yeah. From what I read, it was just it basically just said that if you don't have it for the entire like web page, it can still be vulnerable to some sort of attack.
See, a lot of times what happens is you type your password, and yeah, that's encrypted, and then that password generates what are called one-time pads, where just right at that moment, as soon as you authenticate, the server will send you this one-time encryption pad that will let you encrypt and decrypt information, and essentially there are going to be subsequent transactions that don't involve your password that should still be protected from eavesdroppers. So, yeah.
So I don't see why hackers don't just intercept that kind of very information about the decryption.
Yeah, I mean, that's something that Madeline didn't really address. All of this is possible. Well, I'll let you. Do you know how they actually set up the initial encryption?
Well, they have I know that they have certificates that they have to get. That it's like there's like a public and a private key, which are. It was kind of confusing, but.
I have a good analogy for it, right? So, this has been a problem. It's surprising that it was only solved recently, and by recently I mean in the last 40 years or so. Essentially, let's say that Chris and Chris lives on the East Coast, I live on the West Coast, and I want to send him a secure letter. How do I do that? Well, what was discovered, and this is all done mathematically, is what I could do is I could give the Pony Express guy or whatever, I could give him a box with an unlocked combination lock. So I can give the Pony Express guy this box and a lock that's open. And I know the combination, but nobody else knows the combination. So the Pony Express guy takes the box and this unlocked combination lock to you on the East Coast. You write your note, you put it in the box, you put the lock on and you close it. Now who's the only person on the planet that can get in there? Me. And he takes the box back to me on the West Coast. I know the combination. I open it up, I get the letter. Now, what's clever is inside the letter, what you did was you sent me a one-time encryption cipher. And forever after now, I can just write my letter with the cipher that you sent me, send it back to you in anything that I want, and since you sent me the cipher, you know how to decrypt it at the other end. And forever after, we don't need the combination lock. So we send the open combination lock once, we exchange keys, and then we can talk securely after that. And that process was only discovered in like the 70s, interestingly enough. But it's really clever. And people have wanted to speak in secure ways for centuries, as you might imagine. Popes wanting to talk to kings, and kings wanting to talk to generals, and all that sort of stuff. And nobody figured out this combination lock thing until like the 70s. It's really interesting. So that's kind of what goes on with HTTPS. The first exchange is one of these public combination lock things, and then after that, it's all just simple encryption. You know. Other questions?
So why does that make Facebook slow?
Oh, because all the encrypting and decrypting takes processing time. And Facebook switched over to all HTTPS in January. And I don't know if you've noticed, but it's like super slow and sucky now. And that's why. They need to, crank up their processing power, I suppose. Thanks, man. Okay. You get down to a particular point. I was talking about testing. This web page provides lots of nice examples for you to test. For example, you punch in Rule 30 and you print out the R array, you should get these bits, right? And you punch in Rule 182 and you should get these bits. So lots of things to test here. And furthermore, down at the bottom are actual examples of what you should get when you run Rule 30 or when you run Rule 90 or what have you. And let me show you that with my program. So we've already seen Rule 110. Let's do Rule 188, which should look like this. Yeah, it looks like they're sort of triples in here that kind of go down and to the left. I mean, you know, it leaves a bit to be desired because of the. Oh, you know what? It's also too wide. Yeah, let's do it that way. Okay. What is it, 188? Okay, so that's somewhat reassuring. Perhaps Rule 150, which is this guy right here. Oops. And yeah, maybe I believe that. It's certainly in the ballpark. There's Rule 94. Let's see if Rule 94. There's Rule 94. Yeah, I would say that's Rule 94. 222? Oh, 222 looks fairly boring, yes. Okay. You see these are only sort of the beginnings, so we don't really know what the periodic boundary conditions are or whether they're using periodic boundary conditions. Here are all the rules from 0 to 255. So, and this guy, Stephen Wolfram, maybe you've heard of him. He's the guy that invented Mathematica, essentially, which is a piece of mathematics software. And he really sort of got into these things and actually self-published a book because nobody else was interested. As I mentioned when I first introduced this thing, I'm not sure that they're really useful for anything other than perhaps philosophical kinds of discussions. What do I mean by philosophical? Some of these rules are really boring, and some of them are remarkably complex, like Rule 75. There doesn't really seem to be any kind of pattern here, just constantly changing, and yet, so that one is sort of a random one. And then there are ones like Rule 110. He's particularly fascinated with Rule 110 because it has structure, but it's still kind of random. So it generates lots of these triangles, but there's no real pattern for, you know, where the triangles come, like how the triangles are generated, etc. And he really thought that that was analogous to what goes on in our own universe, right? Our own universe is comprised of these elementary particles which obey the laws of physics repeated over and over and over again, and you get sort of random behavior and you get sort of structured emergent behavior. And he thought that there was some kind of analogy there, but as yet I don't think anybody's really brought it anything past that, really, philosophically. So something to think about, and it makes nice, pretty pictures. See you guys Friday.